Hello, everyone, and welcome to this short discussion where we discuss some paper or research material in physics or mathematics and related to science in general, and that is not often discussed or known in, let's say, the interested public in science. So today, what I would like to discuss about is something that probably people who are into physics are not really aware of. So to put this into context, I'm sure you've heard plenty of situations where a physicist, a popularizer, a lecturer maybe, or a teacher in school would tell you that, for example, it's impossible to explain such and such phenomena by using classical physics or something along these lines. And that the only way to actually explain it would be to use quantum mechanics or some kind of quantum model. And what I want to talk about is precisely about this. It's something called ring polymer molecular dynamics. Here, what I'm going to present is simply some notes and a presentation that has been given during a SECAM summer school by David Manolopoulos, who actually is an expert working on these techniques, who has developed, in fact, and advanced these techniques and that I'm going to talk about, and that essentially, in my view at least, blur the boundary between what people are going to deem classical and quantum mechanical. So, what is this about? Well, the it relies on a mapping, and I'm going here to kind of go towards a little bit. So here's a little bit of, of course, you can feel free to look at this. This person here is describing how we were to be calculating usually the some of the dynamical properties of objects in a general physical system. And basically, there are plenty of things. Some people might see here what are called green Kubo relations, and these are related, for example, they are used to relate the absorption spectra to, for example, the dielectric properties, the complex dielectric properties of a medium, of a material, and so on. So there's a bit of equations here, but that's not what I'm interested in. What I'm interested in is this particular slide here, and I'm going to stop there. What this thing is actually using is what they call here on the classical isomorphism. What is this isomorphism about? It has to do with describing what is represented by this equation here, and this equation essentially corresponds to the quantum statistical mechanics. So what that means is that this is a quantum, and then if you will, you can view that as thermodynamics. It's a bit like that of a point particle in quantum mechanics. Okay, so um, if you take the quantum statistical mechanics of a point particle in some kind of external potential or interacting with other point particles and so on, then this is actually equivalent to the quantum to the classical, statistical mechanics of essentially a bead and spring model like this that is forming a loop. Okay, and this isomorphism is actually kind of quite amazing. It's really again matching a quantum problem onto a classical one insofar as it pertains to equilibrium properties, so time independent properties of some systems. And when I mean time independent, that would be things related to temperature, to the specific heat, things related to this kind of things. Now, what they show as well from their work is that you can also get plenty of things related to dynamical properties as well, but some of the quantum dynamical properties can be lost, and that's it. But the bottom line with this technique is really that you can match a quantum model onto a classical one that is an effective model, and that can be represented essentially as a polymer model. So usually that's why it's called a ring polymer molecular dynamics because people run simulations of a classical system of loops, kind of polymers, and then they can obtain properties about the corresponding um, quantum model. Okay, and so that's a huge deal as far as I'm concerned. I will probably flag somewhere. I've got an actual simulation of a ring polymer dynamics in a harmonic potential. So I can, I will put it in as a link. Um, but what they say here is that what you get from this is you can get. Let me check here, is that what you get in this part with this particular technique is you can get tunneling rates. So if you're interested in like the property for something to tunnel through something else, then actually this can be captured by the equilibrium classical dynamics of a ring polymer. And likewise, if you're looking for 0 point energy, then very easily you can obtain that 0 point energy by using this particular technique. And in fact, that's what we were looking at when we looked at the harmonic oscillator. Um, so I'm just going to stop there. If you want to read further, I will put a link to this particular slides. I think they are incredibly instructive. And it's just to show you essentially that it's not so simple to claim that, such and such phenomena cannot be explained in without quantum mechanics, because there is a mapping, a one-to-one mapping between an actual quantum mechanical model and a corresponding classical model, insofar as some properties only are of interest to us. That would be tunneling, energy, and so on, or equilibrium kind of expectation values in a thermodynamic context, so with like imposed temperature, pressure, and so on. Okay, so that's it. And if you've got any comments or questions, please let me know in the comment sections, please. And otherwise, see you in the next video.